Hi everyone, my name is Greg. I'm a hardware engineer from lowRISC. Previously, I've worked at ARM on A-class processors, on memory systems, and on Broadcom on GPUs, and it's really great to finally be working on some open source hardware, which is what we do at lowRISC. So today, I'm going to talk about Ibex, which is our CPU core. It's a microcontroller class CPU core, two-stage pipeline, very simple, 32-bit. U mode, M mode, PMP, supports EMC and IMC. We wrote this in system Verilog. And it came to us from the Pulp team at ETH Zurich, which I'm sure many of you are familiar with, and where it was known as lowRISC. And we have picked it up and we've developed it from there. And we've done a lot of work into improving the RTL and really doing a lot of verification on it. And so it's being developed by lowRISC, which is the company I work for. We are a not-for-profit company. Work on open source silicon. So we use collaborative engineering. We work with various organizations to build open source hardware designs. And a notable use of Ibex is in our recently announced OpenTitan project that you may have heard of, which is an open source silicon root of trust. And we hope there's going to be many, many more things it's going to be used in. So today's talk is about improving the performance of Ibex. So here, what I'm really talking about is I'm trying to reduce the total number of cycles I've spent executing some benchmarks. So in this particular talk, I'm talking about CoreMark and MBench. CoreMark because, well, everyone talks about CoreMark numbers, and MBench because it's this nice, new, interesting open source benchmarking suite. And I felt it had a great range of stuff to run, and I thought it was a useful thing to look at. You do have to be careful when you're working with benchmarks. You've got to be careful you're not just optimizing for the benchmark only. So you need to, it's very useful to analyze what's going on with the benchmark and use that as a guide as to things that you can then do. You then need to take a step back and think, is this actually generally useful, or am I just making specifically CoreMark quicker? And I would say that the improvements I mentioned here are going to be configurable options in Ibex. So you're going to be able to choose having between a smaller or simpler Ibex core, or you can have a faster core that will be a bit bigger and a little bit more complex. So the trial system that we are running these simulations on is simulating Ibex with Verilator. We've just got a dual-ported memory containing code and data with a single cycle access latency. I feel this is a fair analog of a best-case real system. Obviously, you can get other systems that aren't going to have quite this setup and thus aren't going to perform as well. So, how do we go about working out what's going wrong with our performance? You can, you don't have to do, or I didn't do anything complicated. Literally run some benchmarks, trace the simulation, open up the trace in GTK Wave, and just start having a look around. What you're doing here is you're just trying to look at it, identify interesting behaviors that you can then poke into more and then determine if they're actually causing you performance issues. So it's not a quantitative analysis, but it's just a quick and easy way to get an idea of what's maybe going wrong. So I run CoreMark on our Verilator simulation, and I open it up in GTK Wave, and I have a poke around. And here's a couple of things that I found. So the first thing is having a look at how is this example here, which is a conditional branch. So you can see the instruction down in the bottom there. It's a branch if not equal, and this particular condition is passing. So the thing I have in the red circle there is the first cycle of us executing this branch. We've pulled the two operands out of the register file. We're seeing, and lo and behold, they are not equal. So our result there is a positive. So we are going to branch. But before we can branch, we have to work out where we're going to. So in the next cycle, we use the ALU again to calculate the branch target. So we're reusing that resource, first to compute a condition, and then to do an addition. And then finally, we branch. So this has taken a total of 3 cycles. And during this time, in the second 2 cycles, the processor is stalled because we stay in the same pipeline stage while this is happening. So if we could improve this somehow, then we can speed up our execution. Next thing we can look at is here, loads. And again, we end up stalling on every single load. And the reason for this is, again, our 2-stage pipeline. In the first cycle, we request the data. We have 1 cycle access latency, so in the next cycle, we get it back. But we need to wait a cycle for us to get that data back. So we end up stalling the pipeline again. And we actually have the same behavior on stores. The reason for this is we wait for a response from the store to tell us if there's an error. For example, if we accessed a non-existent address. So we end up stalling for at least one cycle on stores as well. So we've got these stall cycles around branches, loads, and stores, which, clearly isn't particularly good for performance. So we're going to actually do some quantitative analysis now. We're going to use the performance counters to actually see what's going on and dig in to some of the, and try and determine how much this is actually impacting our performance. So we've just identified 2-3 interesting behaviors that are probably slowing us down. Let's see what the actual effect is. So we run our simulation across a variety of benchmarks using these performance counters, and we get some results that tell us how much time we're spending stalled. So this first graph here, on the bottom axis, on the x-axis, you can see the various benchmarks. On the far left is CoreMark. On the far right is a geometric mean of all of these numbers. And in the middle is the mbench benchmarking suite. And what we have here is the percentage of total cycles spent calculating the branch target. So if we go back here, that second red circle there, this is the total number of cycles, percentage of total cycles we're basically spending doing that red circle. That red circle. And you can see, on average, around about 4% of our time is spent doing this. So if we could remove this cycle, we could reduce the number of cycles that we spend doing these benchmarks by around about 4%. And different benchmarks have different amounts of branching, which is, unsurprising. We can do a similar thing for the memory. Note that the y-axis has changed in scale, so we're at, but otherwise very similar graphs. This is the percentage of cycles that we've spent waiting for a memory response, whether that's the data coming back or the response from the on a store from the memory system. And this is a significantly bigger chunk of time. You can see on average that's around about 15%, and then different benchmarks have different amounts of memory activity, so fairly spread about how much performance you can potentially save by reducing the number of cycles you spend hanging around for memory. So we've identified these things. It definitely seems to be slowing down these benchmarks. We can go, is this, if we improve these things, are we just improving benchmarks, or are we improving other things? Well, I think it's pretty safe to say everything is going to use branches and memory accesses. So yes, this is generally useful, and yes, this is a major thing that is slowing down the Ibex core right now. So we need to improve things. So the first thing we're going to do to improve our branch performance is to introduce a new ALU, a branch target ALU. So on the right-hand side here, I have a diagram of the Ibex pipeline, very simplified. We've got our two stages. We have our instruction fetch, so that grabs the instruction out of memory, and then we have decode and execute. Instruction moves into there, and it sits there until it is done, until it is finished and written back to the register file. So if we want to remove this stall cycle around computing branch targets, all we need to do is just add in this second ALU. So rather than spending 2 cycles using this main ALU twice, we are going to use the main ALU to compute the condition, decide whether or not we're branching, and at the same time perform the addition that's going to work out where we're branching to. We increase the area of the core a little bit because we're adding in some extra logic, but we're getting we reckon we're going to get around about a 4% performance gain out of it, so this is probably a good idea. So we do this. Nice, straightforward. But there's other things we need to consider. That's the implementation, so the physical impact of these changes. We're going to add some logic, so that's going to add some area. It's also going to alter the timing, so what frequency we can run the processor core at. So I built an experimental synthesis flow using YOSYS, open source synthesis tool, if you're not familiar with it. And I did timing analysis with OpenSTA. I pulled the 45 nanometer NAND gate library that you can get out of the Open Road repository, and I used this to generate some implementation numbers. I would caution that things like YOSYS and the NAND gate 45 nanometer library aren't going to achieve the best numbers compared to what you could potentially do with commercial tools and libraries. So this flow is not here to say, here's the best numbers we can get out of Ibex for frequency and area, etc. But it is very useful to see relative changes as we make these improvements, and then see where our areas of timing pressure are. See what chains of logic are slowing down our frequency, and thus work out where we can improve things. So here are the results of implementing the branch target ALU. I've just put the core mark results in, but you'll see some mbench results later. And core mark per megahertz, well, that's gone up by about 4.5%, which is what we expected. Great. Area has increased a little bit, but not too much. Great. The problem here is we've just lost some frequency. So our Fmax, the maximum frequency that our core can run at, has gone down by 13%. So actually this means overall we haven't necessarily increased performance, because if we're running at maximum frequency, our maximum frequency has just gone down. So our core mark per megahertz has gone up, but overall we end up with a lower core mark result. We end up with a slower core. So can we do anything about this? This is kind of disappointing. We have this nice little simple change, which seemed obvious, but actually we started going slower. So we need to dig into the implementation and try and work out what's going wrong. Now, Yosis allows you to do this. It's got some nice tools for selecting out logic and examining paths and things, and it produces these wonderful diagrams, which you can spend a very long time staring at. Obviously, it's not particularly easy to just pick out of something like this. So this is a graph of some of the logic inside the Ibex core as produced by the Yosis synthesis tool. You can't immediately go, aha, it's this line here. But you can, with some knowledge of the design, spend some time examining this, have a bit of a think about it, and work out what's going on, which is what I've done. So here's a far simpler diagram which actually explains what we've messed up. So what's happening here, for people who aren't familiar with synthesis and logic implementation, the thing that sets the maximum frequency in your design is based around the length of the longest chain of logic in your design. So you have a whole bunch of logic gates all connected together, and the longer those chains get, the longer it takes for a signal to propagate down and the slower your clock can run. And so what we have here, I've got this grey line which is the longest path in our design. So we start with the instruction, so that's the instruction we've just read out of the instruction fetch stage in the previous cycle, which we are executing. We have a decoder, which is a blob of logic which is working out what we're going to do. It's going to set up the controls for this instruction. This then feeds into the main ALU, which is going to compute our results for us. And then on the right-hand side here, I've got what I've labeled the PC Mux Selection Logic. So what this is doing is choosing where our next PC is going to be, which then feeds into that insta adder O on the right-hand side there. That is the address we're next fetching from instruction memory. And so it's actually quite complicated to decide this because there's quite a few things going on. You might be branching, you might just be going to the next instruction, there might be an exception, there might be an interrupt. We actually have a prefetch buffer which is trying to fetch ahead, which is also affecting the instruction address. So this PC Mux selection actually has quite a lot of things to decide. So it's a reasonably complex blob of logic. And what we've done here is previously, if we were going to branch, we're going to spend 2 cycles over it. So the first cycle, main ALU is going to compute the condition. It is then going to remember whether or not we passed the condition. The next cycle, the main ALU is going to compute the branch target. And what's going to happen is it's going to come out the ALU, it's going to come up this dotted line here, and into this mux, and then out to give us the next instruction fetch address. We have just removed this dotted line because we now have this branch target ALU. And we've introduced this new line here. This is the condition coming out of the main ALU, and it feeds into the PC Mux selection logic. So what we've done is we've taken what was the longest path in the design, namely this dotted line here, and we've added just a little bit of extra stuff onto it because we now put the PC Mux selection logic in there because we're no longer saving the condition, we're using it immediately. And this has slowed us down. So how do we make ourselves faster? Well, we need to have a look at some of the blobs and try and work out what it is we can improve. The main ALU, well, there's probably not much we can do about that. You implement the best adder you can, and there you go. It's as fast as it's going to be. What we can probably do, though, is look at how we're setting up the operands for the main ALU. So we've got these red lines coming in here. These are the control lines, which are selecting what operands we're doing. So what we're going to try and do is make those main ALU operands turn up earlier, so the main ALU result comes earlier. And the problem here that's causing these things to be quite late is because of the decoder. This is a big, complicated blob of logic. It basically controls the entire design. It is trying to work out what the instruction is doing. We need to make it go quicker. So there's a few things I need to fix to do this. Sadly, I've only got time to discuss one of them, and this is this instruction flop fanout. So this thing here, which is what I just called the instruction flop, connects to an awful lot of logic, all kinds of gates. And so in order for it to physically drive all these gates, it needs a bunch of buffering to push that signal out everywhere. And this slows it down quite a bit. So if we could somehow reduce that, if we could reduce that fan out, we can speed up our design. And so what we do is we just make a copy of our instruction flop. We now have 2 of them. And then we split out the decoder. So it looks at a replicated version of the instruction, and then it uses that purely to decide the ALU operand select and then the operation. And then the decode for everything else comes from the other register. And in doing this, we make these red lines appear earlier in our cycle, so all of this returns earlier, and we help fix the path. And as I said, there are some other things we need to do, but I have not got the time to discuss. So after doing this, plus some extra improvements, I've now got a better implementation. Area has actually gone down a bit. I think that's because I've reduced the amount of buffering in the design due to duplicating that register. Sadly, I still haven't recovered the frequency, though. Now, I'm not too worried about this for a few reasons. One, the tools I'm using, Yosis and ABC, the optimizer that it uses, don't actually take I/O timing constraints into account. So the path we've got here is an output path, and there's a constraint on it saying how early it needs to appear. You can't actually feed this into Yosis, so it can't really target the optimization at it. So I think if I had some other tools that were capable of doing this, I could probably optimize this path a lot better, and I could hopefully make the rest of this problem go away. And then the other thing is, this is a microcontroller. You're not necessarily wanting it to run it at the maximum possible frequency. But it is important that we're trying to maintain, we don't just keep adding things that keep slowing it down and slowing it down. So overall, probably a pretty good optimization. For someone who really wants to run Ibex at the maximum frequency, they can maybe want to turn it off, but they can do that because it's a configurable option. Second thing I've done was add a 3rd pipeline stage to Ibex. Now this is actually, I've made this look very simple. This is actually quite a complex thing to do. It's just one of those things, don't really have time to dig into it. But what we've done here is now an instruction goes into decode and execute. It computes its result. Then the next cycle, it sits into this write back stage here. And then it writes itself back to the register file. So this gives us an extra cycle to wait for the result to turn up from memory or for the response to the store. So we lose a store cycle out of loads and stores. And so this is going to help solve our store problems around memory. And as I've said, this is quite a reasonably complicated thing to do. I just don't have time to really talk into all the details about what is going on. And then when I implement that, area goes up, as you might expect, but we've got about, again on core mark, we've got about a 20% improvement in core mark per megahertz. So notable area cost, but it's outweighed by our performance gains. Fmax has basically stood still, so this is the write back stage along with that new branch target ALU, so it hasn't really affected it. It's still those branch target ALU changes that are dominating our timing and keeping us at that Fmax that we have. So, nice complicated graph. Same thing you've seen before, benchmarks on the bottom, core mark on the far left, geometric average on the far right, M-bench suite in the middle, and you can see, and then it shows you our total speed up and a combination of what the branch target ALU has done for us and what the write back has done for us on top of that. And overall, our geometric mean there is 21.3%, so I think that's a really quite significant gain in performance for 7% area, which seems like a pretty good deal to me. Obviously, it doesn't affect all benchmarks equally. Not all benchmarks are memory or branch bound. I think some of these benchmarks in particular are using, say, a lot of multiplies, so that is what's slowing you down now. And there we go. Quick whistle-stop tour through some of the performance improvements I did. If you would like to find out more, you can check out our Ibex repository here on our GitHub. The work I've just been discussing, not all of it is yet in the main repository. So I put up a special Ibex FOSDEM branch in my own Ibex fork you can go take a look at if you want to recreate my results or play around with what I've done. You can also check out lowRISC, got a lowRISC website. We're currently hiring, so if you're interested in working open silicon, hiring both software and hardware positions, do get in touch. And if you have any questions about this work or anything else, then feel free to get in touch and drop me an email. Great, well, thank you very much.